Good day everyone, we from Group 5 would like to present our idea on design and fabrication of a low-cost prosthetic hand model, HydroLimb. Hello everyone, my name is VARSHANNA KUMAR, digits number 2300508. I would like to present the introduction of HydroLimb. The advancement of prosthetic technology has improved the quality of life for individuals with amputations, helping in regaining functionality and independence. However, a sad reality that we need to accept is that not everyone is able to get a prosthetic, as many of these innovation devices come with high price tags and complex design, making it not user-friendly. This project seeks to address this issue by designing and fabricating a low-cost, wheelchair-mounted prosthetic model, HydroLimb, that mimics the essential movement of an upper limb, including shoulder rotation, elbow flexion, and pinch grip. The model focuses on affordability, simplicity, and adaptability, providing a practical assistive solution for individuals with limited hand and arm function. By applying mechanical principles and leveraging basic fabrication techniques, HydroLimb aims to bridge the gap between accessibility and functionality in assistive technology.
So next, in designing the components, we use the base in a rectangular form to stabilize and support the model. So we also ensure that the dimension of the base is accurate to make sure that it can support the weight of the model. So next, we got vertical arm, which is connects base to the arm segment. We also do it in rectangular form to connect the arm component and syringes. Next, which is the arm segment. So in the arm segment, we place some holes as the pivot points and syringes attachment. So next, for the creeper is involved in two claw part, which is functioning in open and close using the hydraulic system.
Hi, my name is Muhammad Aisar bin RUZAINI. My metric number is 23005-133/1. So the design process of our HydroLimb started with sketching and also modeling the individual parts using a CAD software that we use, which is called Shaper 3D. So each component was designed to replicate the functional anatomy as explained earlier. So some of the key features employed during this process included extrusion, shell, and also mirror. We also use fillet to smooth out sharp edges, thereby to enhance the structural durability and safety. We also use chamfer to bevel edges for easier assembly and to reduce material stress point. After we have designed the 3D model, we then exported the STL format file to another software, which is Fusion 3D, for mechanical drawing image.
Okay, so next we move to 2D mechanical drawing. So for 2D mechanical drawing, we use the software of Fusion 360 to generate our mechanical drawing. So the right one is the pinch grip mechanism, which contains of the gripper that have two claw part that functioning in open and close using the hydraulic system. So next, we got the elbow joint, which is the mechanism that support the model and functioning, and it can move also. And then the 360 shoulder movement is showing that the overall of our design, which is the gripper, the elbow, the arm segment, and the forearm and the base.
There are several challenges encountered by us during the completion of our project. Learning to use a 3D CAD modeling application was a crucial step in designing the HydroLimb. As none of our group members had access to a licensed CAD software, we used another software, which is Shaper 3D instead, because it offered a free edu license. While Shaper 3D enabled us to design individual parts, it lacked advanced assembly simulation with constraints. So to overcome this limitation, we exported the individual parts of the HydroLimb into another software, which is Fusion 3D, where we successfully simulated and analyzed the movement of the assemblies. Other issues encountered was about designing the hand of the HydroLimb. One of the key functions of HydroLimb is its ability to perform a pinch grip, where two opposing surfaces mimic the motion of human fingers to grasp an object. However, our initial grip design was non-functional as the surfaces failed to make proper contact to hold an object. So to resolve this, we revisited the design in Shaper 3D and created a new grip mechanism, as shown in the picture here. Only the hand components of the HydroLimb were 3D printed, while the rest of the model was fabricated manually. After collecting the 3D printed parts from the 3D printer lab, we encountered dimensional inaccuracies in the holes meant for the wooden stick joints. The holes, designed to be 2.5mm in diameter, were slightly smaller due to printing tolerances. So to address this issue, we use a soldering iron to carefully enlarge the holes to ensure a proper fit to the wooden sticks.
Hi, my name is NURIN JANNAH, matrix number 22001046, and I will be presenting the whole fabrication process of hydrolim. In creating this prototype, we use materials like straw boards as the main body, syringes, popsicle sticks, wooden skewers, as well as polylactic acid or PLA filament for the 3D printer. The first step in fabricating the hydrolim is to design the prototype first using a computer-aided design or CAD software to figure out its dimensions and shapes. This has been explained by my friends previously. And once we finalize all the measurements, we mark the length and width of each component on the straw boards. Since the material is quite easy to cut, we only need to use scissors and X-Acto knife. For the syringes and popsicle sticks, we use a drill with 2.5mm drill bit to make holes on them. We use this exact size because it allows the wooden skewers to be inserted into the holes of both the syringes and popsicle sticks snugly, because these three materials are what makes the joints movable. Once all components have been cut to size, we assembled them using a combination of hot glue gun and super adhesive glue to ensure they stick properly. We also decided to 3D print the claw part using a 3D printer that is available to use in the engineering faculty, because it allows us to really find out the details on the claw that could not be done just by cutting the straw boards. This makes the gripper mechanism work seamlessly once it was integrated with the rest of the body.
This is the simulation and testing phase of our hydrolim, and it shows insights into the effectiveness of its movement mechanism. For shoulder rotation, as shown in the video on the left, the mechanism it is controlled by a syringe attached to the base and also the vertical body. So when the plunger of the controller syringe is push or pull, the corresponding syringe transfer hydraulic force to enable the vertical body to rotate 360 as shown in the video. And then for elbow flexion and extension, as shown in the video at the middle, it is managed by a pivot joint connecting the upper arm and forearm. It is controlled by a separate syringe. So pushing the plunger will cause the hydraulic fluid to move, flexing the forearm downward, while pulling the plunger extends the forearm back to its initial position. And then the pinch grip mechanism at the end of the forearm is controlled by another syringe. By pulling the plunger, the hydraulic force moves the two opposite surfaces towards each other to grasp an object. In this case, we use a pepper ball, while pushing the plunger releases the grip. Overall, the hydraulic system performed reliably with minimal fluid leakage and also consistent force transmission between the controller syringe and the corresponding parts of the hydrolim.
In conclusion, the hydrolim project successfully achieved its goals in designing, fabricating, and demonstrating a low-cost model of a prosthetic hand powered by a hydraulic system. It has provided a model that can simulate most of the important upper limb movements of the human body, such as shoulder rotation, elbow flexion, and pinch grip among people who suffer from paralysis or weak functioning of their hands. The hydraulic mechanism, along with syringes and tubes, provided a very intuitive, low-cost solution for emulating the operation of muscles. Testing proved that hydrolim can indeed simulate the essential motions of the upper limb. Therefore, it is a practical educational tool and a stepping stone toward the development of future assistive devices.